Thank you very much for the introduction, and thank you to all the organizers for the kind invitation. It's a real pleasure to be here. Thanks for coming. So I will speak, as Roberto told you, about intermediate Jacobians and automorphisms. This is based on two works, one of them in progress with Victor Gonzalez, Alvaro Liendo, and one of them with Roberto. First of all, let me give you some classical motivation, I would say. Then I will give you some kind of historical overview of automorphisms of hypersurfaces, and then at the very end, I think I will speak at the in progress part of this work. So, well, let me motivate you with some classical facts. So, uh, it's very well known that you can study automorphisms of principally polarized abelian varieties essentially by means of linear algebra. And a nice result is that if you have that uh, an abelian variety of dimension g, and this number 2g plus 1 is a prime number, then any automorphism of this principally polarized abelian variety has order at most this prime p. This is the upper bound for a prime order automorphism, for order of an automorphism. Sorry. And very I don't know, naive but very interesting observation is that thanks to the classical Torelli theorem, the same is true for algebraic curves of genus G, since you can associate a principally polarized abelian variety, which is the Jacobian, right? And this information determines the curve. This is the classical Torelli theorem. So a very natural question is, what about higher dimensional algebraic varieties? And there is a very nice result by Adler in the 78 that tells you that if you have the Klein cubic trefoil, so this trefoil in P4 with a very special shape, I will go back to this kind of hypersurface in a few minutes. But if you consider this hypersurface in P4, then Adler computed that the automorphism group is a very nice finite group. It's PSL 2F11. So this PSL group of the over this field. In particular, you can compute the order of this group, and you have some prime factors: 2 to the power 2, 3, 5, 11. Okay, so this is a very nice example, not only because it's a very nice group, but because of the following reason. If you take any smooth cubic trefoil, this a very important work by Clemens and Griffith tells you that you can associate to this variety an intermediate Jacobian. So it's like a higher dimensional analog of this classical Jacobian for curves. Uh, and so this is a, I would say, Hodge theoretic object, which is defined in this way. So this H21 group dual modulo this homology group, and you can compute the dimension, and it's a 5-dimensional principally polarized abelian variety. And not only that, you can compute also that this abelian variety is isomorphic to the Albanese variety of certain surface, a surface of general type with irregularity 5, and which is very geometric, is actually the Fano scheme of lines on this trefoil. So you take all the lines in this trefoil, you get a surface. This surface is of general type, smooth, and of irregularity 5. So in particular, if you take the Albanese variety, it will give you an abelian variety of dimension 5, and this is precisely the intermediate Jacobian. This is very nice. And there is a very, more recent work by Xavier Rouleau, uh, that in this work he proved that the automorphism group of the original trefoil is actually isomorphic to the automorphism group of this Fano surface of lines, and it's contained in the automorphism group of this abelian variety, which is the same as the Jacobian. But and why is that useful? Because when you have abelian varieties, as I just told you, you can use essentially linear algebra to say stuff, and you can actually bound the order of this group, and therefore the order of the automorphism group. uh, Essentially because when you have a automorphism group of an abelian principally polarized abelian variety, you can show that there is a faithful action on the torsion the set of torsion points. So you can play around and you can get effective bounds, and this is the effective bound that you get. So you get again these primes 2, 3, 5, 11, but also you get 7 by means of this computation. And Rouleau actually proved that 7 is not possible, so you cannot have automorphism of order 7. And if you have an automorphism of order 11, this completely characterizes the Klein cubic threefold that I just told you before. So this is very nice. It passes through the theory of abelian varieties, and you get information about the original hypersurface. Um, so one of the main motivations for my talk is how you can extend this to other hypersurface, and what can you say in a very interesting case, which is the case of a smooth cubic fivefolds. So dimension 5 hypersurface defined by a cubic equation. And this is interesting because they also have an intermediate Jacobian, which is now of dimension 21. But I will tell you a few words at the very end, I think. Okay, so let me just fix quickly some notation, essentially. So we will consider smooth hypersurfaces in Pn plus 1.
Pedro,
So
can I have a question?
yes, sure.
These results use Torelli theorem for cubic threefolds, or
Uh-huh.
the
Yes,
question is
yes, 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 yes,
okay.
yes, 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 yes. Yes, I will tell you. Yeah, exactly. That's actually our problem at the very end. Yeah. Um, but you can interrupt me, of course. um, so let me just fix some notation as I just told you. F will be the equation of the hypersurface. It will be fixed. The dimension is n, so the ambient space is Pn plus 1, and the degree is d. Some examples that, of course, you know, but will be useful in a few minutes. Are elliptic curves, so a cubic hypersurface of P2. They are smooth if the discriminant is non-zero. Another nice example are quartic K3 surfaces, so smooth hypersurface of P3 of degree 4. So this 1 degree 4 equation in P3. You can compute that the fundamental group is trivial, so it's simply connected. The canonical class is also trivial, so it is actually a K3 surface. And you can, of course, imagine any equation that you want. You can put some random coefficients in such a way that it's smooth. But there is a very nice construction from linear algebra that I want to tell you, only because it will be uh, also used for in a few minutes. So at this point, it seems a little bit artificial to do this, but you will see why I'm doing this very soon. So pick some. So consider this sixfold P3 times P3, and inside consider some bilinear equations, 4 of them. So if you take general enough coefficients, each when these are general hypersurfaces in there. So if you take one equation, H1, it will give you a fivefold, then a fourfold, threefold, and then a surface S. So you pick 4 of these equations, you cut them, and you obtain a surface inside this sixfold. And by means of linear algebra, you can study what is the image through the projection. You have 2 factors, so you can project on the first one and onto the second one. And you can see from this equation, essentially, that a point in this P3, the first P3, belongs to this image if and only if you can solve this linear equation where you fix the variable x. So this is a matrix time vector y equals 0, and you need a non-zero solution because you are in the projective space, right? Which turns out that the determinant of this matrix has to be 0. But this matrix is a matrix of linear forms. So it's a 4 by 4 matrix of linear forms. And so therefore the determinant is a degree 4 polynomial in these variables. and it defines a degree 4 surface on this first P3. Of course, this is completely symmetric, so you can have the same thing on the second factor, and you get another surface of degree 4 in P3. Yeah, just by fixing the other variable. And you can imagine, I don't know, by classical Bertini type computation, that if the coefficients of these linear forms are general enough, then first of all, the original surface S is smooth, but moreover, the projections are actually isomorphisms. So you have a very nice picture. You start with an S inside this P3 times P3, and you get two a priori different, two ways to see this surface inside P3 by means of the two possible projections. Okay, so keep that in mind. This is a nice example. Um, Another very classical example of hypersurface that I know people in this seminar knows very well are Fermat hypersurfaces, which is this Fermat equation equals 0. This is smooth. Another very important that I just introduced to you at the very beginning is the Klein hypersurface, which is the fixed variable to the power d minus 1, then the next variable, then you pick this second variable to the power d minus 1, then the third variable, and so on. And then you close this equation and you get this very nice hypersurface, which is smooth. It's a nice exercise to show that this is smooth as long as the degree is at least 3. For degree 2, you need to, it's a quadric and it depends on the dimension. So a very first question that you may ask is that if you have two hypersurfaces inside this projective space, when these hypersurfaces are isomorphic, first of all, as abstract varieties, and when this isomorphism is induced by the ambient space, when they're isomorphic as embedded varieties. Okay, so this is the first question. I will tell you the answer very soon. And of course, a very important case is when the varieties are the same. And in this case, we're looking at automorphisms as abstract varieties, right? This is the automorphism group of your hypersurface X. Um, so I will spend a few minutes answering this question. Actually, the answer is very nice, and this related with these two examples that I give you just before, the elliptic curves and quartic K3 surfaces. Um, but before that, let me give you some very simple examples that also will be useful to fix some notation. So the first example is that the projective space, of course, itself has a linear automorphism group. This is a nice exercise, I don't know, in Harshern. When you are learning algebraic geometry, you learn that the automorphism of the projective space are essentially matrices up to, of course, scalar multiplication, so PGL. And therefore, you have a natural subgroup of the automorphism of X, which is the automorphisms which are induced by matrices. By automorphism of the ambient space. So this is the subgroup of linear automorphisms. Uh, for instance, if you have the Fermat hypersurface, you can look at the permutation matrices. These are linear, of course, and they are automorphisms of this hypersurface because of the symmetry of the equation. But and you, of course, the first question that you may ask is it true or not that all automorphisms are linear? And the answer is no. There are two nice examples. The first one is the elliptic curves. When you have an elliptic curve, you can fix a point. For instance, let me in my example, for instance, let me check. For instance, this point Q. I'm sorry about that. And you can construct an involution using any point essentially in the following way. You pick a point X you look at the line from X to the point that you fixed in this picture Q, and you look at the third point in this intersection. And of course, this is how to say an involution, because if you start with this TQ of X, then you go back to X using this method. And it turns out that this involution is linear if and only if this point that you pick up is an inflection point. For instance, in this picture, if you take the inflection point at infinity, this one, you know that doing this kind of geometric construction, you get the actual reflection from this axis. So this is of course linear. You take the variable, a comma b to a comma minus b, which is of course linear. But if the point is not an inflection point, you get non-linear automorphisms of an elliptic curve. And you know that there are only finally many inflection points. So most of the automorphisms of an elliptic curve are not linear. So this is an example. And another example is quartic K3 surfaces. If, as I just explained to you, there is a way to construct quartic K3 surfaces from linear algebra by means of these projections, and it gives you they are given by determinant of some matrices, and you can use linear algebra, actually Kramer's rule, to construct an isomorphism of degree 3. It's just the 3 by 3 minors, right? You have two ways of compute this determinant, and you can show that this is actually non-linear. It cannot be how to say, this is a really a non-linear example. You cannot play around to linearize this. It's actually non-linear of degree 3, and therefore the automorphism group of this quartic K3 surface is non-linear. Okay, so this is two nice examples, and a very, very classical result by Matsumura and Monsky in the 60s tells you that these are the only examples. Let me just read you this statement. If you have any smooth hypersurface, even algebraic curves of degree at least 3, then first of all, the group of linear automorphisms is finite. I should mention that this result was proven by Camille Jordan at the very end of the 19th century by hand, using explicit computations. It's a huge work of Jordan, which was rediscovered by Matsumura Monsky by other methods. Secondly, if you pick a general hypersurface, and here by general I don't mean of general type, I mean if you have the moduli space of hypersurfaces of this fixed dimension and degree, and you pick a general one inside this moduli, then the only automorphism that you get is the identity. So most hypersurfaces don't have automorphisms. And the last result is that if you are not an elliptic curve and you are not a quartic K3 surface, then every automorphism is linear. So these are actually the only counterexamples, and all the rest have linear automorphisms. So this is very nice because you can do essentially linear algebra to compute interesting stuff. Okay, so this is for the one variety alone. So as I just told you, I promised to you that I wanted to give you a glimpse on this question. When two hypersurfaces are isomorphic as abstract varieties, or as embedded varieties, and so on. And this is this is very surprising, but this is quite recent. Um, of course, there are many. This is based on very classical results by Nether, Lefschetz, Matsusaka, Mumford, so on. But this final answer that I'm presenting to you here is essentially due to Ogiso and Shimada Shioda and as you may see, it's very very recent. And they,
Pedro,
yep,
Pedro. So
yep,
this general means Zariski open set in the parameter
yeah,
space,
yes,
or
yes, yes,
okay?
yes, yes. That I mean to general. um, yeah, sorry. Yeah, I'm just telling you that if you, this is very well known and very classical for a single hypersurface, so X, right? But you, of course, you may ask about what about two different, a priori different hypersurfaces. And as I just told you, it's quite surprising that the answer is quite recent. Um, if you have two smooth hypersurfaces, a priori of different degrees, um, and you suppose that these varieties are isomorphic as abstract varieties, right? So you may have a very weird isomorphism between x1 and x2. Then a posteriori, the isomorphism has to come from the ambient space, except maybe in the following cases: elliptic curves and quartic K3 surface. So I will say that this is a combination of a lot of works, and the quite recent result is this last part, and the existence of K3 surfaces which are isomorphic, but not the. I mean, the isomorphism does not come from the ambient space. And this is essentially the work of Ogiso and Shimada Shoda. Okay, so this is, and this completes this picture. Okay, so just to summarize, sorry, it's a lot of information. Um, well, essentially, if you are not looking at elliptic curves and K3 surfaces, everything is linear. All the automorphisms are linear. If you pick a random hypersurface, as Hossein points out, the automorphism group is trivial. So only at a closed Zariski open set of the parameter space, you may have automorphisms. Um, so let me tell you more about this. Fix some notation as well. Um, so if you fixed a dimension and a degree, you can have a natural parameter space, which is just take all the all the hypersurfaces. You don't care if they're smooth or not. All the hypersurface of degree d on dimension n. This is of course a projective space as well. This is the projectivization of this linear system. And the subset of smooth hypersurfaces is an open Zariski subset, and the complement is a divisor, is the discriminant divisor. For instance, in the case of elliptic curves, is the discriminant that I showed you. And so we will be interested in smooth hypersurfaces, and moreover, we will be interested in hypersurfaces which are not elliptic curves nor K3 surfaces because of the result of Matsumura and Monsky. Um, in other words, because in this case we know that every x in this open set has finite automorphism group and linear automorphism group. So you can see everything inside this PGL n plus 2, the number of variables, and it's a finite group. And you may ask, of course, uh, if you can, I don't know, if any finite group can arise as the automorphism group of an hypersurface of fixed degree and dimension, and the answer is no. There is a very nice argument, I would say topological argument, using the Ehresmann theorem, which tells you this Ehresmann vibration theorem implies that all of these hypersurfaces are diffeomorphic. In particular, they're homeomorphic, and therefore any topological invariant that you may look at is constant. And well, in particular, this cohomology group uh, is does not depend. I mean, the this group is a free abelian group whose rank does not depend on the degree, and I mean, it's constant once you fix the degree and the dimension, and you can actually compute it. This is the rank. Okay, so you have a topological invariant and a very nice thing happens here is that using the formation theory, you can prove that the automorphism group acts on this cohomology group faithfully. Um, you can find this in a very nice work, which is in a very nice book, sorry, by Daniel Huybrecht about cubic hypersurfaces. He gives a very nice proof of this. And once you have a faithful action on a lattice, then you can invoke some classical results about lattices by Minkowski, and you can show that there, once you fix the rank of the lattice, I mean this number if you want, there are only finally many finite subgroups of this orthogonal group. Very concretely, once you fix the dimension and the degree, there is a universal constant such a way any automorphism group is bounded by this universal constant. I mean, there are only finally many possibilities. So this is and I mean, kind of the dream of this of this how to say uh, of people studying automorphism group of hypersurfaces is to determine this constant. I would say it's a very nice question. I will tell you some known results about this, and I will. I mean, kind of a. I cannot say a conjecture because there are not that many evidence, but I mean, based on the examples that we have, which are not a lot of them, one can guess that the this biggest automorphism group is realized by the Fermat hypersurface. But of course, this is a guess based on very few examples. I I cannot even say that this is a conjecture. I don't know. It's what we have up to now. But I will tell you a little bit about this. So as I tell you, the main question is since you have a finite list of groups, which of them can arise as automorphisms of a smooth hypersurface of degree d and dimension n? All of them, or I mean, up to this bound, or there are some restrictions. So this is what I'm going to talk about in the next few minutes. And then a very natural way to how to say do a devisage on this question to simplify this question somehow is using the hierarchy of finite groups, which is the following. I mean, you have all finite groups, of course, and this is the main question. But you can ask yourself some sub questions. You can ask for example about which I don't know cyclic groups can arise as automorphisms of hypersurfaces, as subgroups of automorphisms, of course. Um, of course, not every cyclic group is abelian, so you can enlarge your category into which abelian subgroups can arise. For instance, this group is abelian but is not cyclic. You can also ask about nilpotent groups. For instance, this quaternion group is nilpotent but not abelian, and so on. You can I don't know, try to relax your category of groups until you get to the all finite groups. This is kind of a very natural way to think about this question. And I have to tell you that this is mostly open in all of these categories. I will give you the spoiler of the final answer. The only thing that we know at this point is that first of all, the general hypersurface has trivial automorphism groups, so you can say something about this. Um, and you can actually determine which cyclic groups appear, and that's pretty much it. I mean, that's the final answer. In this generality, this is what we can say. Um, but once you fixed some dimension and degree, you can start to say more interesting things. And let me give you some glimpse on the historical how to say on a historical overview of the on these results on once you fix the degree and the dimension. So I should say that kind of the first higher dimensional complete answer was given by Dogachev and Iskovsky, 2009. They studied smooth cubic surfaces because of other reasons. They were studying the Cremona group of the plane Cremona group, and in order to do so, they had to study some rational surfaces, after some Del Pezzo surfaces, and along their study of these surfaces, they had to study the automorphism groups of cubic surfaces. Sorry, and they determined all possible G that can appear, all possible maximal subgroups. In other words, any other automorphism group of the smooth cubic surface has to be a subgroup of this G, and there are actually 11 non-isomorphic possibilities. So this is a very nice answer. This is a full answer, but you have to fix, of course, the degree and the dimension. So this, I mean, fix this question in that case when n equals 2 and d equals 3. Now, if you look at this general picture of finite groups, and you look at the very first, most simple category, which are cyclic groups, then a first answer was given by Victor Gonzalez and Alvaro Liendo, um, this year, 2011 and 13, and they show the following: if you have a power of a prime, p to some power alpha, and you assume that this number is relatively prime to the degree of your equation, and the degree minus one. Okay, so for instance, for cubic hypersurfaces, prime to 3 and 2, then you can determine which of them appears as automorphism groups, or in other words, which of these cyclic groups are admissible. And the criterion is very nice. You can do it by hand. It's very constructive. You have to look at this equation: uh, 1 minus the degree to the power L mod 1 equals 1, sorry, mod q, and you have to look at all possible L from 1 to the number of variables that you have, and you have to check if this equation holds or not. If this equation holds, then there is an automorphism of this order. If not, then it's not admissible. So this is another way. Sorry to get to do this, but so this is another way to reprove this result of Rouleau that I just told you at the very beginning. That 7 is not an automorphism of cubic triples. Much more. You can say a lot more for prime order automorphisms and power to the prime order automorphisms. Um, of course, assuming that this condition holds, that q is relatively prime to the degree and to the degree minus one. Okay, so this is a kind of a first approach to this question. Um, Another thing that I should mention is that the case of curves on P2, which is also kind of surprising that is so recent, has been settled very recently by Pambianco and Harui. And the answer is kind of the one of the, how to say, this is one of the evidence about this kind of conjecture that I just told you about this universal bound. This is actually the the single evidence in all degrees when you fix the dimension. To be more precise, Pambianco and Harui prove the following: when you have an elliptic, sorry, not an elliptic, and a smooth plane curve of degree at least 4, you are, of course, you don't take you don't look at the elliptic curves, because I just told you that they have weird automorphisms. So you restrict yourself to degree 4 or higher. Then the automorphism group, the order of this group is at most 6 d squared, with equality if and only if the curve is the Fermat curve. So this is the what we think that should happen in higher dimensions. Unless there are, I mean, unless you have a D is very sorry, unless D is 4, in which case there is a very classical result by Klein that tells you that the degree 4 curve with largest automorphism group is the Klein quartic curve. So of course it's an exception. So in this case, the automorphism group is PSL2F7. So as you may remember, at the very beginning, I also told you that the automorphism group of the Klein cubic threefold is kind of the same group. It's PSL2F11. So there is something happening here with the Klein hypersurface. It's kind of a mystery. I will tell you at the very end. And another famous example is
Pedro, just
yes,
do you claim that in these examples,
yes,
hypersurfaces with maximum automorphism group are isolated? They do not have moduli,
yeah,
something like
yeah, something like that. Yeah, yeah, something like that. Yeah, this is what we think
that.
that should happen.
But
Uh,
this is expected to be in general. I mean, these hypersurfaces with maximum automorphism group have to say in the moduli space. This means that after quotienting by PSL something,
yes,
they must be isolated point. No.
yeah, and I believe that it should be actually the Fermat hypersurface.
Okay.
But based on the examples, I mean, this is true, for instance, for cubic surfaces. This is true for curves, thanks to this work of Pancampianco and Harui. I mean, in higher, I mean, not of the in degree 4 is not true. In degree 5 is true, and in degree six, sorry, is not true, because there is this Wiemann sextic with automorphism A6. But degree 7 and higher, this is true. Um, so this is the only result that we have once you fix the dimension and you let the degree to be free. So the other results that we have, once again, you have to fix the dimension and fix the degree. So for instance, if you fixed the dimension to be 3, so you have threefold, and you fix the degree to be 5, so quintic threefold. Um, this was studied by Ogiso and Yu. This is very interesting, as you may know, because they are Calabi-Yau hypersurfaces. This is the first example of a Calabi-Yau threefold, and they determined all possible automorphism groups G that may appear, and there are 22 non-isomorphic groups of maximal order. All the rest are subgroups of these 22 examples. So this is a very nice answer. And once again, the the most symmetric hypersurface is the Fermat quintic threefold. Another example, which is based, of course, of the work on the work of Adler that I told you at the very beginning, and a recent work by Wei and Yu. Another nice example, so is the cubic threefolds. Once again, and quite surprisingly to me, this result is really new. Um, Although the cubic threefold have been studied for long time, right? Um, they determine the maximal subgroups, the maximal groups of automorphism. Sorry, and there are 6 possibilities for the maximal G that can appear, and all the rest are subgroups of these 6 possible G. And once again, the most symmetric cubic threefold is Fermat cubic threefold. So this is the only evidence that we have. Another one that I think I didn't write it. Yeah, I didn't write it. Another example are cubic fourfolds. They are very nice because they have a hyperkähler variety associated. I won't enter to the details. Maybe at the very end, we'll say a word about this. But in this case, for cubic fourfolds, so degree 3, dimension 4, Also, the answer is that the most symmetric cubic fourfold is Fermat. This is a work by Radulasa and Chiwei Cheng, this guy here, that has another very interesting work. I think now is published. I mean, it's accepted but not published. So, but in the archive is was on the 2020. So this Chiwei Cheng determined all possible cyclic groups that can appear as automorphisms of hypersurfaces. In other words, the work of Cheng answered this part of this diagram. So this is okay, and essentially all the rest is open. So this is what we know at this point. Um, Unfortunately, the criterion is how to say, it's not that simple to state. It's very nice, but very how to say, combinatorial. I would say for sure you can do it on a computer, but it's not as simple as this criterion for which is of course in a much more restrictive case of power of primes. Here Q can be anything, okay? And this is the full answer for cyclic groups. Okay, so now let me tell you about some new results that we have, uh, which is some liftability result. So I didn't tell you the techniques that you can use to obtain this kind of results, about the classification of maximal groups of automorphisms, and there are essentially, I will say, two techniques, more or less. One technique is to look at the automorphism group and look at this action and the action on some discrete thing, so a lattice, for instance, pretty much inspired by this thing that I told you before, that the sorry to get up, that the automorphism group acts faithfully on this cohomology group. For instance, in dimension 2, for a surface, you have that the automorphism group acts faithfully on H2. And actually, this is what Dolgachev and Iskowski used to study automorphism groups of cubic surfaces. So in that case, since a cubic surface is isomorphic to the blow up of the projective plane at 6 points in general position, this lattice is very well known. It's a set 7, and it's not only a lattice. You have an intersection form, and you can study the automorphism group acting there, and then classify what can happen. So this is one way, and the other way, which was actually the starting point for us, was used by Ogiso, Wei, Yu, and this is the following. You know that any subgroup of the automorphism group can be seen as a subgroup, a finite subgroup of matrices of PGL something, 5 in this case, for instance, for the case of threefolds. And so you can ask yourself, when this group has a lifting to, not to GL, no, PGL, sorry, but to GL5. I will tell you right now what is a lifting, but the point here is once you can lift your group to GL, then you can use representation theory. I mean, actual representation theory. As you may know, the projective representations are more complicated than actual, I mean, classical um, representations. So here you can use all the character theory. Anyway, I mean, a lot of stuff that you have from representation theory to look at invariants and so on, and try to classify what can happen. This is the global idea. So this motivated the following question: when you can do this, and first of all, what is a lifting? So for us, a lifting is the following. Uh, as I told you before, you fix the equation f, and you look at a finite subgroup of automorphisms, right? Finite subgroup of matrices, and you say that as a finite subgroup of GL is a lifting of your original group G if when you restrict the canonical projection from GL to PGL, well, this restriction is an isomorphism, so the groups are the same. And moreover, you have an induced action of this or the elements of this G twiddle on polynomials, right? And you ask that this G fixes the equation. It's not only a multiple of this F, but it's actually the same F. It's not only an semi-invariant, if you want. It's an actual invariant. So this is the notion of liftability, of lifting, and I mean this work of Ogiso, Wei, and you, as I just told you, is based on the side when you can do this. And once you can do this, you can use all the representation theory machinery to give your classification results. Okay, so this is the kind of big picture that motivated us. So let me give you two examples. You can show that the Fermat hypersurface, for instance, always have a liftable automorphism group. Since essentially you know all the automorphisms, you can do this by hand. However, if you look at this Klein hypersurface that I just introduced before, this Klein hypersurface, uh, and you assume that the degree and the number of variables are not relatively prime, so they have a common factor. In particular, they have a prime common factor. Then you can use this prime common factor to produce a non-liftable automorphism. Sorry, I should mention that this liftability condition is independent of the choice of coordinate. I mean, if you have a one equation and you change the by a means of a linear automorphisms, the liftability is preserved. I mean, the liftability of not liftability is preserved. So okay, so this is a small parenthesis. So once you have a common factor of the degree and the number of variables, you can produce a non-liftable automorphism of this Klein hypersurface in the following way. First of all, since this prime number divides the number of variables, you can cook up some packages of large P. And which kind of packages? Well, the this root of the unity, primitive P root of the unity, to the power 0, 1, 2, up to the power P minus 1. So you have a package of length P, and since P divides the number of variables, this fits up, and you can have an actual um, how to say matrix, and you can show simply by replacing that this is an automorphism of this hypersurface, this Klein hypersurface, and it's not liftable because it's not invariant; it's only semi-invariant. Okay. Okay, and we proved that this is the only bad thing that can happen, and this is our main theorem with Victor and Alvaro. We show that an hypersurface, the whole automorphism group, if liftable, if and only if the degree and the number of variables are relatively prime. And so this is the full answer of this question. We can retrieve, we can give alternative proofs to the some results by Ogis or Wei Yu in this way, and have a new results in different degrees and dimensions. And maybe I should mention that in order to do so, we had to prove some improvement of the previous result by Alvaro and Victor. Uh, but with some extra restriction. Of course, this is not as precise as the result of Zheng, but it's somehow easier to. I mean, it's a complementary work. It's a particular case, but it's easier to state, I will say, and it's a tool that we use to prove this main theorem. So it's quite complementary. Well, this is the statement. I won't read it, but essentially, The new part is that in the previous result we needed to have that p was relatively prime to the degree and to the degree minus one, and here we can say something precise in these new cases. So this is a very combinatorial, very precise criterion. I won't give you more details. Um, Maybe an example is, I think, is better. If you take cubic hypersurfaces, which are very nice, of course, you can determine which cyclic groups of power of a prime order and of prime order and p to the r order are admissible and liftable. So just to tell you, once again, just let me take a look at the threefold case. Once again, you can retrieve the fact that the 7 is not admissible for cubic threefolds, but also you can bound this number 2 to the power r, I mean, up to 4, and 3 to some power, and this power can be 0, 1, or 2. And in a similar way for, I mean, for any degree, essentially. Um, and you can use this also to give a, I mean, I think that the main application that you have for this is that you can give a effective bounds on some CLO piece of groups of the automorphism group. Let me just recall you. Once you have an abstract group, a finite group, a CLO piece of group is a subgroup of order p to the r, and this r is maximal. This is just the definition of CLO piece of group that you may learn in a, I don't know, algebra course. And we have again a very nice criterion, mini combinatorial criterion. You fix the prime, you fix which does not divide the degree and the degree minus one, and you define this number. This is again related with the previous result by Victor and Alvaro, but it's a number that you can compute. And if the liftability assumption is satisfied, in other words, the degree and the number of variables are relatively prime, then you can give an effective criterion in such a way p squared does not divide the order of the automorphism group. In other words, uh, if you have a p CLO subgroup, then it has to be trivial or this cyclic group. So this is much more powerful because we're not only bounding the order of automorphism, but p CLO subgroups. Um, Once again, let me just give you some cubic examples. Um, uh, you can bound these numbers now, not only for a single automorphism, but for the whole automorphism group. Um, so you can say a very precise thing about these exponents that can appear. Notice that in the case of cubics, most of the time there are 0 or 1. Unfortunately, we don't have control about what happens for p dividing d and d minus 1. This is kind of the, well, if you want an open question, what can you say in these cases? Um, okay. Um, well, since I have a very few minutes, let me just give you a very short sketch of the proof. Sorry about that. So, I mean, one of the key points I will say that is that if you have a, let me just give you this key remark. This is kind of the starting point of everything. Um, if you have an automorphism of order q, or say the order is a prime number, for instance, here, and this prime divides the degree, such that it divides the degree. If this automorphism is not liftable, then this prime has to divide the number of variables, and therefore d and the number of variables are not relatively prime. This is what's kind of the starting point, and the rough idea is that if you have a non-liftable automorphism, then you can assume that this is the case. When you look at the some lifting, uh, the induced action of the polynomial on the I mean on the degree d polynomials, does not fix this f, is a multiple of f, is an actual semi-invariant, then, well, you can look at all the eigenspaces of this automorphism phi twiddle, and you can show that that this condition on non-liftability and the smoothness of the hypersurface implies that all the eigenspaces has the same dimension, and therefore the number of variables, which is the the dimension of the ambient space, right, the vector space B, then you projectivize, has to be p times the dimension of any of these eigenspaces, and then you get the result. Just to give you an example, this is exactly what happens here in this counterexample. All the eigenvalues come in packages of the same size. This is the general picture, actually. Okay. So, well, this is the case. Then we prove that. I mean, if you have something non-liftable, then you have necessarily the degree and the number of variables are not relatively prime. And on the other side, if these quantities are relatively prime, we cook up essentially by hand a lifting. Maybe the only thing that I think is quite nice, and I would like to stress, just to give this very very short idea of proof, is that in the case of an isomorphism of order p to the r, in such a way p does not divide the degree and the degree minus 1, and does not divide the number of variables, so a very particular case, we can actually show a stronger result. We can show that there is a lifting, but moreover, this lifting is not only in GL, it's in the group SLB. This is actually very interesting because for the case of cubic fourfolds, as I just told you at some point before, there is an associated hyperkähler surface. Actually, sorry, not surface, hyperkähler fourfold, which is obtained by as the Fano variety of lines of this fourfold. And this condition of being in SL translates into the fact that the induced automorphism on this variety is symplectic. Since it's a hyperkähler, sorry, there is a symplectic form, and this condition of SL translates into the symplectic condition, and therefore we can actually give some results about the order of symplectic automorphisms of this kind of hyperkähler fourfolds. And we retrieve also some known results that were studied before by Liendo by means of other methods. Okay, so this was the very very rough sketch of the proof. And just to finish, let me give you a very short. Let me give you a few words about the case of cubic fivefolds, which is a work in progress. As I just told you, as I told you at the very beginning, these surfaces, these hypersurfaces, sorry, also have an abelian variety associated, an intermediate Jacobian, which is a dimension 21. However, as Hossein pointed out, Torelli theorem is only known for generic x. This is a result by Donaghy, and is not known for any x. Similarly, if you want to use this connection between the Jacobian and the Albanese of some surface, you can do this thanks to a work of Colino, but only for general x. Actually, this S is the Fano scheme of planes now inside this X. And this thing can be singular for some X's. For instance, for the Klein cubic fivefold can be singular, is singular actually. So it's hard to do things using, a naive approach. However, we can say some stuff in the case that the Jacobian is extremal, is an extremal principally polarized abelian variety. What does it mean? It means that the higher order automorphism actually appears. As I just told you 1 hour ago, um, the maximal order is 2g plus 1, which in this case is 43. And so therefore we are looking at fivefolds with a 43 order automorphisms. And by a result of Alvaro and Victor, the only cubic fivefold with a order 43 automorphism is the Klein cubic fivefold. And therefore, the intermediate Jacobian has an automorphism of order 43, and therefore is extremal in this sense, and moreover has complex multiplication. And we are in the middle of showing that, and I will finish with this, that first of all, and in opposite to the case of cubic threefolds, the automorphism group of this abelian variety is not what we thought, PSL2F43. So this was a little bit disappointing at the first, I mean, at the very beginning, because if it were this group, then we will have some, I mean, counterexample for Torelli theorem, but it's not the case. So, but that's life. But however, we can show using the work of Benama Bertin that the automorphism group modulo plus minus the identity has to be this thing, this semi-direct product with M7 or 21. Moreover, the liftability implies that the automorphism of the original variety can be seen here inside, and therefore we are almost there, determining the automorphism group of this very special cubic fivefold, and we believe that the answer has to be 7. And I think I will finish here. Sorry about the extra time.
Pedro, maybe well, this about this that the maximal group
Mhm.
was supposed to be isolated. You told me that
Uh-huh.
it must be Fermat. So I think there are no so much results about the loci of hypersurfaces with a fixed type of group as automorphism.
Mhm.
Or is there any? I mean,
The only thing I know, for instance, is that if you have some, let me give you, for instance, when you look at these cubic hypersurfaces, when you fix, I don't know, one prime number, I don't know, five, for instance, you can cook up families of these of hypersurfaces with this with order 5 automorphism, and you can count the dimension, and that's pretty much it.
uh,
Um, essentially by looking at invariants that have a smooth representant.
Actually, it might be also interesting that you and Roberto a little bit think in this way. For
Mhm.
example, automorphism is an algebraic cycle in the self product of the hypersurface. And
Uh-huh.
then there, the self product of the hypersurface, you have the notion of Hodge loci and so on. And actually, this kind of realization is a kind of Hodge conjecture. You have the topological data, which is the group, and you
Uh-huh.
want to realize it. And I mean, okay, anyway.
Uh-huh.
Uh,
Yeah.
yeah, okay, I'm done. I think.
Thank you. I should say thanks for your attention.
And Pedro, and do you know what is the problem when you are regarding quartic surfaces and P3 and elliptic curves and P2, because many of your results does not hold in this case. So
ah, yeah. This is okay. That's a nice question. So let me give you uh, a positive and a negative answer. I mean, the negative answer is that in the case of quartic K3 surfaces, as I quickly mentioned here, the automorphism group is not linear. So the full automorphism group may have non-linear elements. So that's the bad side of the picture, I would say. However, of course, you can restrict yourself to the linear automorphisms and try to say something. Classify the maximal subgroups there, and I believe that there are partial results in the case of quartic surfaces by Pambianco.
Mm.
Uh, I don't think there is a full answer, but there are some examples under some restrictions. Yep.
Okay, but so we could ask with any automorphism of the quartic surface could be derived from a general a general rational map, for example, of P3,
Yeah, yeah, yeah. I
which
got it.
does not to be linear, for example.
Right, yeah, right. Yeah, 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 yeah. Mm-hmm. Yes. Mm-hmm. 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 Right, right. Yeah, yeah. I mean, yeah, that's a good question. Yes, because you can also in all these cases you construct models where these groups act. So once you have this model, you can look at the subgroup of, I mean, your favorite subgroup, and you can see the action inside this model. Right? Yeah, yeah, yeah. Yes, 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 yes,
Mm.
yes, yes, yes. Mhm. Right. Uh, okay, so this is okay, how to produce these models. Okay, I didn't tell you, but this is a good question to to show you something at the very end. One of the main tools to produce the explicit models is to show, like in the middle of the proof, that the automorphism group is generated by, in many cases, by how to call them, like generalized permutation matrices. Are permutation matrices, ho- but instead of one or zero in each entry, you have zero or a root of the unity. And once you have matrices which are very special of this form, you can cook up by essentially by hand invariants. This is the way, and this is related, for instance, with this result, which is the evidence that more or less tells us that this number should be 7, the automorphism group of the on the Klein cubic fivefold, is because if you have the Klein hypersurface of degree at least 4, unfortunately, we can show with another method that the automorphism group has to be generated by this kind of generalized permutation matrices, and using this we can determine the automorphism of Klein hypersurfaces. Once again, very surprisingly, this was only known for curves and not in higher dimension. I mean, how to say, except for some fixed dimension and degrees, it wasn't known for all Klein hypersurfaces, the full automorphism group. And the proof is based on this technique. Um, I don't know if I answered the question. ah, okay, I will stop sharing.
Mm.